Yeah.
How many more tests?
So
I'm going to miss you.
we're going to look at normal distribution this week, and next week we'll start the last topic. So normal distribution, you all know about the bell curve, you all heard about the bell curve. We all know it is a distribution, but we're going to do a little bit more study on it, alright? So now, you should be able to work out a standard score by the end of the lesson. Hey, that's the class going. Alright, go ahead. So you need to understand what the normal distribution model is. You should be able to use appropriate notation and parameters. Define the probability density function, and then understand the features of a normal distribution model, including symmetry, the 68%, 95%, and 99.7% rule, and be able to calculate probabilities from a normal distribution model. Quite a bit to go through today, and I have got 3 lessons planned on normal distribution. I'm going to start something new next week. Alright? So, let's think about comparing 2 sets of marks.
What? 27?
Oi, stop! I want to get through the lesson as soon as I can. So now, if you think about 2 method tests, if John scored 27 out of 40 for the first test, and 30 out of 50 in the test 2, has he improved? Has he studied enough?
Don't know.
You don't know, do you? Because we really can't tell, especially if you're looking at this. We are looking at just the raw marks. We can make it into percentages, but still it's not good enough. Now, what if I know the mean of the whole cohort and the standard deviation for the cohort? Can we then compare in that sense? So we're looking at it in the terms of the whole cohort now. So where is John's placed in terms of the whole cohort? Alright? We know the mu, which is the mean, and the standard deviation sigma. So let's think about standardizing the score. Now, if you have missed a test last year, year 11 or year 12, if you miss a test, we use this procedure to actually fill in your missed test. See what your ranking is in terms of standard score, and then we work backwards. Alright? Now, you need to know how to standardize the data. To calculate the standardized score, or the standard score, is the raw score take away mean divided by standard deviation. You need to know that. Alright? So, if the raw score is equivalent to mean, what happened? So, x equals to mu, which means 0 divided by sigma, a standard score of 0. Alright? So if it is less than the mean, which means you're going to negative. So what happened is, if you look at the standard bell-shaped curve, the peak here, that is the mean. Alright? So with that, when we standardize the score, this is x minus mu divided by sigma, it will be 0. Alright? Then the one standard deviation is 1 standard deviation away from the mean.
Yeah.
And then we've got 2 standard deviation. This is sigma. This is 2 sigma. 2 sigma. Away from the mean. And then we've got the 3 standard deviation away from the mean, which is 3 sigma, 3 sigma.
Yeah.
Alright? So now, a raw score equivalent to the mean will give a standard score of 0. A raw score above the mean will give a positive standard score. So anyway, from there, that's positive, that is negative. Alright? Any raw score below the mean will give you a negative standard score. So therefore, the higher your standard score is compared to the mean, the more positive your standard score is. Alright? The lower your score is compared to the mean, the more negative your standard score will be. Which means, if you go higher and higher, you have improved, you probably have got better results. And if you go lower, you would have not as good a result. So if you think about this sort of distribution in terms of exam mark, you will want to try to get as high as you can. Alright? So that you are away from the mean. So now if we calculate for John, the first two methods test, John scored 27 marks and 30 marks. So we can now work on the standard score. So the standard score told me that John is the Z score for test 1 is 0.8. Or the standard score is also called Z score. And for test 2, the standard score is 0.5. So in that case, we can conclude that John actually did not improve based on the standard score. Alright? So like if you missed a test last year, we use this sort of process. We look at the test or we look at the investigation. We work through your standard score for the couple of tests that you have done, take the average, and then fill in the one that you've missed. Alright, so let's, example 1, let's do that, please. Let's work out the standard score for test 1, 2, and 3 for Sam. And then express her test score as standard score, and then rank the test score back to us. So you know is the score minus mu divided by sigma. Alright? And you can do a sanity check. If the score is higher than the mean, it is positive. Score is lower than the mean, it's negative. Alright? So you can see that in this situation, there would be a 1 negative and 2 positive. Alright? So working that out. Test 1, 1.45, 1.4 sigma below the mean. Alright? 1.4 standard deviation below the mean. So test 2 is 0.5 standard deviation above the mean. And test 3 is 0.8 standard deviation above the mean. So if you want to score from the best to the worst, it will have to be 3, 2, and 1.
Yeah, 3, 2, 1.
The further away from the mean, the better it is. The higher, the more positive away from the mean.
I am under the wood.
Alright? Means the better the score is. Alright? So it's 3, 2, 1. Now, example 2. Max has set 3 maths tests and was absent for 1 test.
Yep.
The results for the 3 tests by Max is whatever it is. You need to be able to calculate Max's standard score for each of the tests. Alright? This is what we do. This is basically what we do for someone who missed a test. So there are only 2 investigations for year 11 and year 12. If you miss one investigation and you did really well in the other investigation, which means
Maybe I should skip the next one.
oh, you got to have a legitimate reason to skip the next one.
Yeah.
He's sick.
Oh, you can't be unless you're sick for the whole week.
No, I'll be there, sir. Don't worry.
Yeah, I trust you.
How many more do you have?
You've got 1 more investigation and 1 more test.
You got one more test as well. One more test as well.
Yeah.
Yeah, on this stuff.
Alright? So, you should be able to do A and B pretty straightforward.
Yeah.
Alright? So you got the 3 test Z score. Test 1, test 2, test 3. If you want, you can use the subscript Z1, Z2, Z3. Alright? Once you work out all 3, the mean is there. Alright, so to work backwards for test number 4. So we know that the standard score for 4 will be the average of these 3, 0.1947, and that's the score. And you know that for test 4, the cohort mean is 69, and the standard deviation is 13.1. So therefore, x take away 69 divided by 13.1 is the standard score for test 4 for max, the average. So therefore, we can work out x is 71.55. Now this is 72. So what you need to think about is, in this sort of question, we don't have half marks. So therefore, you got to round it up. In that sense, in the exam, you got to round it up.
Yep.
Okay, happy with that? So you should be able to work on your Z score, and this is pretty straightforward. Now, we come to normal distribution. So there are many natural occurring examples of continuous data that when collected and graphed in a histogram form a symmetrical distribution, where the frequency decreases as we move away from the mean and increases when we move the other side of the mean. Alright? Both frequency decreases when we move away from the mean. Alright? So this sort of shape can be fitted into bell-shaped curve. This is what we know, bell-shaped curves. We use it a lot. So, example of normal distribution, result and assessment, it should generally fit that. So if you think about it, somewhere here would be your A plus. Alright, so that would be your A, sort of. And then around here would be your B, that would be your C, that would be your D. And that would probably be your E and F. Something like this if you think about the results. So this is a distribution, result of assessment. And the weight of paired dogs is normally distributed. Height of males / female, measurement errors in experiment, they are all sort of standard normal distribution. So it's called the normal distribution or the Gaussian distribution. Either word is used. Now, the notation. We say that a continuous random variable x is normally distributed with mean of mu and standard deviation sigma. We denote using the following. X with the little squiggle is normally distributed with the mean of mu. And now, note, we use variance when we write the notation. We don't use just sigma. So this one, you got to be very careful, is sigma squared. Alright? The variance is sigma squared. You got to be careful because you might be given something like sigma squared, like 3 squared, I'll show you later, or 25. So here, for example, instead of writing 5 squared, I use 25. So you need to take the square root to find the standard deviation, whereas this one, the standard deviation is already there. Alright? So be careful, watch out for the notation. It could be a number or it could be a number squared. So if it is number squared, that is straight away the standard deviation, whereas that you need to take the square root. Alright? So here, this notation means that the variable x is normally distributed with a mean of 10 and a standard deviation of 5. And 4, 3 squared means that the variable x is normally distributed with a mean of 2 and a standard deviation of 3. Right? Now, that's a notation that you need to know.
Yep.
The PDF and the normal distribution. So the probability density function of a normal distribution with mean of mu and a standard deviation of sigma is given by this. Alright, the equation is from negative infinity to infinity. So if the probability that x is between 2 points, C and D, you integrate between C and D. Alright? Don't have to write all this down, but you just need to make note of that. Understand that the probability function is normal, the probability distribution function for normal distribution is this. Alright? Now, the properties of a normal distribution. The bell-shaped curve is symmetrical and it's a bell shape, which means it's symmetrical by the mean. When you fold, this tail should fully cover that tail. Alright? This tail here should fully cover that tail, or that tail should fully cover this tail if you fold it in half. Now, properties of a normal distribution, asymptote of y equals to 0 because I am using the standard score. Alright? You could say that, y equals to 0 is not, what did I say? Symmetrical by x means so wrong. Asymptote of y equals to 0 is the x-axis. So it will go on and on and on and on, but it will never cross your x-axis, y equals to 0. Symmetrical about x equals to mu. I read the wrong thing. So I could use mu or 0 here. If I use standard score, this will be symmetrical about 0. But if I don't use standard score, I use the data, it will be symmetrical about the mean. Alright? So the mean, the mode, and the median for the normal distribution coincide. Alright? So that bit here depends on whether you use the mean or the actual mean or the standard score. If it is standard score, that will be 0. If it's actual mean, it will just be the mean. Alright? So you need to know the difference. The width is actually determined by the standard deviation. Alright, I'll show you a slide a little bit later. If you think about, say in the exam, you've got a mean of maybe 50 and the standard deviation of 20, which means the variation of the mark is very high. Alright, whereas if you've got a standard deviation, mean of 50 and standard deviation of 5, which means it's very close. Like everyone is really close to 50 marks. So the width of this is determined by the standard deviation. The point of inflection of the curve are located on 1 sigma either side of the mean. It's definitely there. That's it. There's no other point of inflection. Think. The larger the value of the standard deviation, the greater spread of the curve. So you can see that if sigma is large, it will spread out a lot further, and the peak will be further will be down by a little bit. Now, one thing you must know: the total area under the curve has to be 1.
Classic.
It must be 1. All right. So let's have a look at the curve by itself. So in this case, both of them, the mean is 100. The standard deviation for the blue line is 15. So you can see that one standard deviation will be somewhere here for the blue line. So this is 115, this is 85. 2 standard deviation, 85 minus
30.
15, which will be 70. This will be 2 standard deviation, 130. This will be 145. This will be 70 minus 15 is 55. Alright? So you can see that it is closer. Whereas if it is the next one, the dotted red line, 1 standard deviation away from the mean is 130, so it's somewhere there. So it's spread a lot wider.
Yeah.
Alright? So you should know this is the same mean but different standard deviation. Look at the shape. 1, the closer it is, this is higher. Standard deviation, when it is bigger, larger standard deviation, it's a lot wider. Alright, now, what I'm going to do is introduce a term called the standard normal distribution. If you took all values of x from our normally distributed continuous random variable and standardize all the score, alright? So we actually locate the z-score for every single one. What we do is we have to standardize the standard normal distribution. The standard normal distribution, the shape should be the same as this. The only difference is what is here. All right. Here, the mean is 0, whereas the mean is the mean of the set of data. When you work out the standard deviation, here you know that one standard deviation is equal to 20. All right. Now, in the standard normal distribution, you just work out that is just 1. All right. That is one standard deviation. What is happening here? Should I know? All right. So you need to, you can see that here, that is one standard deviation, the way you can see the actual data. Here, you are just looking at one standard deviation away. So one standard deviation is 20, 20. Two standard deviation is 40, 40. But here on the standard normal distribution, that is just 2. It's a reason why we actually use the standardized score. Basically, in the olden days when you don't have your class pad, we actually have to standardize everything before we could work out the probability. I'll show you the table in a few minutes. It's a pain in the bum doing that. I remember doing that. All right, so here you've got the green bell-shaped curve. You've got the mean of 1010 and the standard deviation of 20. Whereas the standard normal distribution, the mean is 0 and sigma is 1. So if you've got different sets of data, lots of this. If you standardize it, it should all, if they are all proper normal distribution, it will all fit in here. So with the standard normal distribution, we can work out the area under the graph. All right? Using a table. So this is the two different way of writing it. One, x is normally distributed, and this is, that should be 20 square there. I missed a square, all right? That should be 1010 and 20 square, or 400. Whereas for z-score, it's, the mean is 0, and the variance square is 1. So I leave it as 1. I don't have to write it as 1 square. Whereas that, I should have written it out as 20 square. My fault. I'll change it a little bit later. There should be a square there. Can you change it in your note, please? There should be a square there. All right? Now, for the standard normal distribution, you know that mean is 0 and sigma is 1. Rearrange it. This PDF is all independent of the mu and sigma now. All right? There's something that is independent from the mu and sigma because you know that we have standardized everything. All the data is into just one graph, which is a standard form. So can you use your class pad to evaluate that, please? From minus infinity to plus infinity. All right? You should be able to do that, and you should be able to get an answer. It should be 1.
Yeah.
It should be 1. If you use your class pad, that should be just 1. All right? Because it's the area under the curve. The area under the curve is 1. Now, go back to this curve again. The curve is has an asymptote about the x-axis, and it continues indefinite in one direction. All right? There is very little area under the curve for that value that's greater than 3 standard deviation from the mean. Very, very little area.
Oh, 68.
So the area under the bell curve between 1, 2, and 3 standard deviation from the mean respectively are very commonly used in figures. So I'm going to show you the next bit. Let me explain.
So I got 0.9.
All right. So here, the peak at the mean value of 0. And then when z is equals to 1, it represents the position of the score that is 1 standard deviation above the mean. Alright? Or minus 2. It represents a score of a score that is 2 standard deviation below the mean. That's all. Now, can you use your class pad to evaluate this, please? Class pad has rounding errors. It goes on and on and on. It's a maybe a rounding thing. Use your class pad to evaluate this tree, please. So 1 is between 1 standard deviation, minus 1 standard deviation to plus 1 standard deviation. 1 is from minus 2 standard deviation to 2 standard deviation, and then 3 to 3 standard deviation. Alright? You can pretty much see the answer from my slide now.
Yeah. 68, 95, 99.7.
Yep. So, what it is you've got these three numbers here. 0.6827, 0.9545, and 0.9973. Alright, I'll explain that. So, the probability of a randomly selected individual from a normally distributed population being within 1 standard deviation, anything that's between minus 1 and 1 standard deviation, the probability that's happening between those 2 points is 68%, all right? Or 68.27. But for ease of calculation, we use 68%. Between 2 standard deviation is 95%, or 95.45. Like I say, for those two, for the sake of calculation, without calculator, we'll just use 68 and 95%. Whereas the standard deviation, 3 standard deviation, is 99.7%. So you can see that generally the data, all right, 99.7% of the data is within 3 standard deviation.
Yeah.
All right. Anything above that, it's not really, in a way, it's really small, the area. All right. We are only going to concentrate this area between between minus 1 sigma and 1 sigma, from negative 2 sigma to 2 sigma, and minus 3 to 3. So you can see that we are only interested in those areas in this stage. All right. Now, okay, if you look at this, although on the diagram I've shown you 68.2%, 95.4%, and 99.7%, we are only interested for the first two, forget about the decimal. Alright? You're using the 68 and 95% and the 9% of the rule. You know that it's symmetrical, right? So how many percent, what is the probability if you pick someone, an individual? It's between the mean and 1 standard deviation. 34, because it's 68 divided by 2. So it's 34. Alright? Now the yellow area, it will be 95 divided by 68. 95,
minus
take away
68.
68, and then divided by 2, correct?
Yeah.
So you've got 13.5%, the yellow area.
Yes.
And then finally the red area is 99.7, take away 95% divided by 2, 2.35%. So these are the numbers that you'll be using quite a bit. You could be combining between those two, could be combining between those three, could be between those here, 13.5 and 34, plus 34, so on and so forth. So if you know the area well, you would be able to work out the question later. Or just use the 68%, 95%, and 99.7% rule. Alright, so let's have a look at the first one. The example 3, you've got given standard normal distribution. of between 0 and 1. Of mean of 0 and standard deviation of 1. Alright? So for the first one, how would you calculate if z is less than minus 1? You don't have to integrate. You're not going to integrate because you're using the 68%, 95%, and 99.7% rule. So you know between here, alright,
98 divided by 2.
here, that would be one standard deviation that is 34%, right? Sorry, 68%. Two of them, that would be 68%.
Usually 50, take 34.
Alright? This is 68%. Right? Now, this area should be the same as that area, correct? Yeah? So you could use 100% take away 68%, which means those two left, and divide it by 2. Or you can use 50 take away 34. It's the same thing. Alright? So it's up to you how you want to do it. But I use 100 take away 68, which is 16%. So therefore, probability of z less than minus 1 is 0.16. Normally for probability we give 4 decimal places, but in this case you work out to be 16%. That's it, 0.16. So what about the next one? Less than 2. Alright, if this is less than 2, you know between here and here. Alright, that is 95%, correct? Yeah? So it's 95% plus 100 take away 95% divided by 2, because you are adding that area in. Agree?
0.5 plus
Yeah?
95 and 2, right?
Whatever.
Yeah.
It's 97.5%.
Yeah.
Alright? 0.975. So the next one, can you try the next two? The next two you got to manipulate a bit more.
Because you add. Oh yeah. It's okay. I need that as well.
Yeah, bro.
Now, in fact, if you go back to the previous slide, if you already know this area here, it's pretty straightforward. Is that 95% take away 68% divided by 2? That's all. Alright? Which is 13.5%. I've shown it to you just now. So the next one, you've already know this between 2 and minus 3. And you know that this is 68%. So it's 68 plus 13.5%. Or you could do it that way, or you could do 95 take away that bit. It's still the same. And therefore, the probability is 0.815. So you need to be able to use the area. Alright, so let's consider this, a normal distribution of normal distribution of 10 as the mean and 3 as the standard deviation. Can you fill in the
Because the middle point's
dashes here, please? What are the numbers here
Middle point's
associated
10.
with the dash? What would that be?
4,
So you know that
4, 16.
this bit here will be
Yeah.
1,
10, right?
1 and 19. Yeah.
Yeah.
Because the mean is a 10.
4 and 16.
And then you got to
Good job,
plus
Byron.
both sides. 1 standard deviation minus 3 and plus 3. You've got 7 and 13. And then 13 plus 3 and 7 take away 3, or 10 minus 6. 2 standard deviation away. And then finally 3 standard deviation away. And therefore, you can calculate that, or just write that down. Alright? So basically, instead of using the standard normal distribution curve, now I'm using this curve, and I'm using the actual value, knowing the distribution. Alright,
No, it is.
Let's go to the next one. So what is...
Standard deviation is 3. No.
I'm showing you some of the answer. Use the 68%, 95%, and 99.7% rule to determine each of the following probability for a normal distribution of mean of 10 and standard deviation of 9. Alright? Now, the most important thing, listen, for you to do this is sketch the bell-shaped curve. It doesn't have to be perfect, but sketch it. Once you sketch it, you know where the standard deviations are. 1 standard deviation away, 2 away, and 3 away. And you can see that you are shading certain area. If it is greater, you are shading that area. And you're looking at that area only.
No, I got 0.025.
Alright? So you know that this is greater than 16, from 16 to infinity. Greater than, this is 2 standard deviation. So therefore, can you work out this area? Yep. You could work out that area because you do know that between here and here is 95%. Alright?
Yeah.
So,
So you did
100 take away 95% divided by 2 because it's this end.
So you did 99.
Yeah.
That's
So
different.
therefore,
Yeah.
no, it's wrong.
Yeah,
This
it's
is part B.
different. It's different.
So therefore, it's 2.5% or probability is 0.025. So B is actually, again, I draw the same thing, just sketch it, and that's the end. Alright, so this time is take away 99.7 divided by 2. It's 3 standard deviation away.
Wait, how is that? Oh, yeah, true.
True? Yeah, because you're looking at one tail only. So that's that tail over there and that tail over this side. Alright? One is we are looking at the right tail, the other one is the left tail.
Yeah.
Alright.
Yeah.
And then between 4 and 19. 4 and 19, you know that 4 is 2 standard deviation away and 19 is 3 standard deviation away. So you do know that, for example, here, it will be 95%, right? So 99.7 take away 99 divided by 2 with this small area here.
Yeah.
And then you add it together, and therefore you got 0.9735.
I didn't look at it. I didn't. Trust.
This is the last example for the day. There should be some exercises from Clark and Sadler for you to do. Alright?